Good morning, everyone, and good afternoon, good evening to anyone who may be joining us from around the globe. So my name is Pete Schulte, and I'm the lead application engineer here at Markforged headquarters, located just outside of Boston, Massachusetts. So today we will be covering hybrid part production, particularly in metal and composite 3D printing, specifically as it relates to Markforged products and product offerings. So we'll be discussing exactly what constitutes a hybrid part and the instances of when and why we would decide to create a hybrid part, as opposed to just printing a single piece, and the advantages that hybrid parts bring to a wide array of applications. Often when discussing hybrid printed parts, we have a tendency to focus on combining printed composite and metal parts together. However, there are far more varied types of hybrid parts than just those, and we will cover several main varieties. Multiple composite parts with one another, composites with off-the-shelf or conventionally manufactured hardware, composites with printed metal, metal parts with added hardware, metals with other metal printed parts, and then we will finish up by discussing when it is a smart idea to hybridize a part and when it likely is not. And honestly, the when not to is just as important as when to design a hybrid. After that, we'll finish up with any questions that you all may have. So note that we're going to save those until the end. However, please do feel free to populate the chat with questions as we go, and then we'll address as many of them as we can at the end. So first off, what is a hybrid part? Well, in general, a hybrid is a combination of two or more objects, specifically of different origins. In this case, combined to form a single part, rather than just separate pieces coming together in some manner of a functional assembly. Many of our customers are using our printers to create standalone parts. They'll import a design file in the form of an STL from whatever CAD program they're using, configure their part within our slicer software, Eiger, send it to their Markforged printer, and then we'll get a completed part off of the print bed. And many times that process is sufficient. However, through hybridization, it is possible to achieve many things that a single part in a single print just can't. The parts can be improved, the parts can have higher performance, and they can achieve things that can't be achieved by traditional manufacturing or with just a standalone single printed part. So some reasons to create a hybrid, and there are several. Primarily is supplemental properties. So if we're dealing with just our base polymer, Onyx, our flagship, for instance, there are specific material properties associated with Onyx and with our print process, as well as the print orientation and the geometry involved. So now those can all be altered by changing the part orientation on the print bed, by changing the overall geometry or the infill pattern of the part. However, if we really want to step outside of the bounds of what just an Onyx part or just a metal printed part can offer, what we need to do is look at combining these materials with each other, with themselves, and with other materials. Things like adding our continuous carbon fiber alongside a metal, or adding carbon fiber along with Kevlar in order to blend those pieces together, or adding things like off-the-shelf hardware. This can offer options like larger parts and assemblies. Prior to the release of our FX20, we at Markforged were often asked about the prospect of larger print beds, expressly with the desire to print larger monolithic parts. Well, many times that's not necessarily the best path forward, and bigger is not always better. We will talk about how to get larger parts and assemblies, and not only how to achieve them, but how to make them better than if it was just a single press print. You can also have stronger parts, so making composite parts stronger, reinforcing them even further beyond the true composites that we do print today. Other potential factors would be speeding production. So if it was a situation where you're only intending to print one piece to get your final part, if you can potentially split that part and print the sections in parallel on multiple machines, if you have access, that can potentially accelerate the process and reduce your overall time to part, particularly if it's a critical application, a time-sensitive application. And finally, simplifying the process. Sometimes there are going to be critical features that just can't be achieved through a single press print. and may require a lot of post-processing. Hybridization may solve those problems as well. So first off, composite and composite hybrids. In many cases, we can create assemblies, larger parts, or optimization of parts in part properties and geometries by printing multiple composite pieces and then combining them together. So here is an example of a demonstration part that we have from some of our current and former members of our application engineering team. One of our former apps engineers created this bridge that you can see here with one of our current application engineers, Nate Sampson, standing on top of it. This was specifically created to demonstrate the concept of ideation and ingenuity in manufacturing. So again, when the concept of maximized single print beds comes up, and the desire for just kicking off a very large single part, single print, which could be a 5-day, 10-day, maybe even 2-week long print conceivably, there's an increased potential for failure endemic to that process. And not only that, but you're significantly limited by the resulting properties of the part. In virtually any FFF style printing, interlayer Z strength is a perennial issue. That's why positioning and orientation on the print bed is so important. Now, if this part were done in a single print, we would not have been able to take advantage of the varying orientations for printing, of varying routings of Markforged continuous fiber capability, which is our core strength. In something like this, where you have a full assembly, splitting it into multiple pieces allows for increased potential for success across the entire build and decreases the potential for a single print failure, power interruption, or anything else that might impact the overall build schedule. It allows for disseminated manufacturing or the utilization of a potential print fleet in order to accomplish larger parts and assemblies concurrently so that you can have your finished part in less time. So rather than having a 5, 10, 15-day long print, in order to make a very massive part, we can instead, if we have the benefit of that multiple printer situation, print successfully in a much shorter period of time. It allows for better overall physical properties and strength within the part as well. Other instances where we may want to split a composite part into multiple composite prints are instances where ideal surface finish is necessary in particular locations, or preservation of geometric features is paramount. Print time may be needed to fit within a specific production timeline, or if certain portions of a part need strength in particular planes relative to other portions of the part, we can alter that geometry and the orientation on the print bed in order to properly route fibers in multiple planar directions within a single part, and then we can join them afterwards. So here's a better picture of that bridge. The total assembled part was approximately 45 to 50 printed pieces. All of them, again, printed, and was able to be assembled in a relatively short period of time, and can be easily disassembled as well, despite the apparent press fit. With the calculations that we performed on the overall design, based on the print parameters and the fact that we did use continuous fiber reinforcement within the part, in this case, carbon fiber, the bed of the bridge itself is calculated to hold upwards of 1,000 pounds. Now, that would not be possible, particularly if you have any sort of like shifting weight situation or dynamic loading case in a single print, even on a much, much larger print bed, certainly not in FFF style plastics. Not to mention the further increases in speed to completion by reduction of the support structure that would otherwise be necessary to print this part monolithically. In fact, this whole bridge was printed with virtually no supports at all. So we've reviewed applications where blending multiple prints of the same material or combining polymer parts with fiber reinforced parts can be a benefit. Now, looking at alternate plastics, Markforged has released a flexible TPU material to our available print library back in September of this year. While our primary claim to fame is the strength of our parts, the addition of a consistent, flexible, and compressible polymer allows for addressing of an expanded set of challenges. This capability is multiplied even further when combining both strong and flexible parts. So this part here is a printed TPU gripping surface interlocked via dovetails with a precisely printed onyx base to create a single blended actuator. This was designed and utilized as part of a FIRST robotics challenge to allow a robot to easily grip and lift target cones. Additional uses for our TPU material are the incorporation into parts that need varied stiffness or need to be very strong, but also non-marring to the objects and surfaces with which they must interact. We have a number of other customers that are using our TPU in very, very similar situations on production lines, in manufacturing, where preservation of the parts that they're working on are absolutely critical. Next, we have composites with the incorporation of hardware. So this is actually the most common usage that we will typically recommend and see with our customers, particularly when printing in composites. Incorporating off-the-shelf hardware allows for several benefits. One, better supply chain or standardization of other materials and better utilization of the printers as well. So if you are not having to print every single piece of your assembly, you only need to print the ones that are most ideal for additive, and you can use off-the-shelf hardware, potentially reducing your overall material cost and allowing for some standardization of whatever hardware is involved. Secondly, there are certain features and parts that really just shouldn't be printed. So things like large shafts printed vertically or bolts for very small threaded components, or that just aren't suited to our process of either metals or composites. Additionally, this allows for the incorporation of threads in a reliable manner into composite parts. Yes, we can print threads, but if you're looking to mate a metal thread or a metal bolt with one of our composite printed parts, it is best to do so with a heat set insert or a helicoil or some external hardware. This is especially important if the threads are meant to support multiple threading cycles. If you need to assemble, disassemble, reconfigure things, then the repeated threading of standard hardware into a composite part may degrade over time. So utilizing this type of hardware can extend the usable life of tools like that. Furthermore, it allows for strengthening of composite parts by incorporation of that hardware. Things like pins, bearings, sheet metal, magnets, weights. So they're all manner of hardware can be incorporated into a print. And this is an area where Markforged particularly shines because we have the capability to pause our prints easily and incorporate that hardware and resume the print, allowing for complete encapsulation and incorporation of those hardware elements into our parts mid-print. Making this even easier is the support override feature that was released to Eiger earlier this year. So that's a capability that's in the internal view when working in Eiger and allows for turning off supports in specific areas where in the past the supports would need to be printed and then would need to be removed prior to actually adding that hardware in. This speeds the capability of adding in that hardware mid-print and allows for reduced usage of material, reduced time between pausing and resuming your print, and so on. So here's an example where you can see heat thread inserts or threaded inserts being placed into a part. Dowel pins, standard pins, shafts being inserted into parts to act as metal wear surfaces in an otherwise composite part. This allows for longer part lifespan compared to just the composite alone, but still maintaining the lightweight and the low cost without having to go to a completely metal printed part. So here's a part that one of our other engineers, now one of our product managers, put together. It's a drill bushing handle that's commonly used in aviation and aerospace industries. These are parts that typically have a long lead time or are sourced very precisely through specific approved vendors and are also critical to the execution of high-value operations and programs. If I'm working on a helicopter, I certainly want to make sure that I'm drilling in the right place. When parts like this are not available, it can hold things up significantly on the production line, resulting in protracted delays and significant financial impact. The ability to print these tools, utilizing small off-the-shelf hardware, allows for the maintaining of planned production schedules. Next are parts consisted of both printed composites and printed metals. These are the ones that often come up and come to mind when we're speaking about hybrid printed parts, and also bring to bear the most of what Markforged has to offer with our true continuous fiber composite prints, as well as our printed metals. So these serve the purpose of taking a composite part and strengthening it even further with a conformal or custom metal printed piece, possibly something that may be very expensive if it were traditionally manufactured, whether as an off-the-shelf component or as a truly custom metal piece. Printing such a piece in metal can reduce lead times or reduce cost, particularly if machining is done outside of house, or allow for quick turn iteration for things like prototypes, necessary custom tools, or for keeping a digital inventory of parts like this wrench here, for instance, where you have a lightweight onyx and Kevlar wrench with a replaceable box wrench head at the top. So this allows for parts with modularity. So imagine, if you will, having multiple different wrench heads, perhaps including custom heads, in order to fit whatever the current application requires. This prospect becomes even more impactful when considering things like standing up tool shops globally, or supporting an overall supply chain infrastructure across maintenance facilities or other aftermarket facility work. This mitigates the need to ship tools from one location to another if they can potentially be printed at the point of need, perhaps even on demand. So this may also come from the other direction, where we may consider printing a metal part, whether traditionally manufactured or printed, where we see our continuous fiber composites replacing aluminum parts quite often, and then lightweighting that part while maintaining high strength, particularly in sections that are wear surfaces or areas that require very high strength of metal. Here's an example of a designed hybrid part that exhibits both the use of printed composite for stiffness and rigidity, lightweight, and lower production cost, as well as faster production time, and then also utilizing the custom nature of what we can print in metals for the actual wear and contact surfaces. On top of that, you can even see the hardware incorporation into attaching the two pieces together, as well as joining the composite part sections and the locating pins to affix the tool to the robotic arm on which it will ride. So now we have metals with hardware. So this is another one that may not immediately jump to mind, because if we have the ability to print metal, why not just print metal as one whole piece? Well, particularly with the Metal X print system and process, metal prints can be limited in size, specifically by the sintering process. Now, metal parts can be split up into multiple pieces, but then it becomes very important to look at that print process, the throughput, and the time that is necessary in order to provide those finished parts, and decide if it really should be printed all in one piece, or if there are certain parts or features that may not be ideal for the metal printing process, or that may be able to cheaply, easily, or quickly be purchased off the shelf, or simply machined and assembled together to form the necessary part. Here's a case where we have an alignment actuator for, in this case, a railway cutting guide. So it actually assists in the cutting of the metal rails on railways in commercial and industrial rails. And it includes a specific cam surface that features a custom profile. Originally, this was machined from a single piece of billet steel. So a significant waste of material by the customer and a significant amount of time in order to produce it as one piece. Now, we could possibly print it, but it would take a lot of time in post-processing and cleanup involved if it were printed in the lengthwise orientation, which with the Metal X process would be necessary for both the sinter process as well as the most advantageous printing orientation. If it were printed vertically, hypothetically, it would not be ideal for either, even if it did fit into the process envelope, as parts like large high aspect ratio shafts are not really well suited to the sintering process of the overall, and even if they're properly supported, and that would add to the supports and the post-processing required. So instead, in this case, it's far faster, less expensive, and overall more advantageous to simply print the complex cam surface and then to machine a raceway into an off-the-shelf steel rod, allowing for the two pieces to lock together into the necessary configuration for function. So now we have metal-to-metal hybrids. So there's a great amount of potential here, especially with the vast variety of applications to which our printed metal solutions can be employed. So combinations like combining our tool steels with our stainless steels with very high strength portions of a part or tool with the remainder maintaining its high corrosion resistance. Copper, Inconel, or other high performance materials or specialty materials mated with more standard materials when the performance of those specialty alloys are perhaps not necessary throughout the entirety of the part. Now, one important factor to consider when mating metals to metals is that of surface dissimilarities and corrosion. Galvanic corrosion from differing metals is a point to consider. However, there are often ways to mitigate such concerns. Other reasons why we would combine metals with other metals would be factors like preservation of critical features and surfaces. Such a case would be one where maybe we have a stainless steel part, but there are critical surfaces on both the top and the bottom of the part, and solutions like post-machining may not necessarily be ideal, or those facilities might not be available. So we may be able to print the part in multiple pieces and then assemble it afterwards in order to maintain those tolerances, features, or surface finish requirements. It also allows for solution targets such as reduced print times and or fleet usage if we do have multiple printers to pull on. So if we have a customer that has multiple metal printers and can utilize a split assembly in the desired application, and then can assemble the part to completion at the end of the process, then it can potentially increase speed to part, as well as allow for batching of prints through both the wash and sinter processes to even further reduce time, cost, and overall touch time. Modularity and prototyping are also additional aspects to consider here as well, where you may have a blank or something like this. With these V blocks that are designed to hold a particular piece of hardware or a device under test, or a piece of machining work that's being processed. That necessary conformal shape may change from part to part, from product to product, or it may be in the development process and the tool or fixture may need to change as the product or as the process changes. However, the bulk of the assembly may not necessarily require modification. So if it's possible to evaluate the design and pare down to the minimum amount of modularity that's necessary in order to successfully support the process, or in order to support manufacturing across however many products or production lines are necessary, then it might be entirely possible to combine multiple printed metals with inserts or printed inserts into machined bases. In this particular case, the problem was approached with both printed metal inserts as well as printed composite inserts, depending upon the situation that was necessary. And this was a case where the metal was actually less expensive than the carbon fiber composite and stronger, particularly because the design iteration allowed for the reduction to a minimum of what was necessary for printing for each application. So that pretty much sums up the majority of the different permutations of the types of hybrids and parts that we could consider coming out of our processes here at Markforged. Though it is not an exhaustive list of all the ways in which they can be used, however, it does represent the majority of what is capable within the digital forge. Now, when are the times that we really should hybridize, and when are the times that we really shouldn't? So when we have a situation where we need the advantage of multiple properties of multiple materials, whether it's metal or off the shelf, or whether it is our continuous fiber composites, or whether it is just polymers, then that would be certainly a prime candidate. And when print farms or print fleets are available as well, that brings even more to bear in favor of hybrids being a significant advantage, especially when such resources are available in a configuration that's not necessarily set up in such a way as to be booked for continuous production or full queues or maximum uptime processing long strings of parts, but are kept to be able to react quickly and add agility for things like prototypes, initial product development, or an initial product ramp. However, in lower volume production scaling, this approach does lend itself to rapid turn production of hybrid assemblies, where each part can be rapidly completed via a total fleet utilization of discrete components. Additionally, this sort of approach also serves to de-risk the production of each part by minimizing the impact and delay of any potential failure in that process of printing. And then when we have strong parts that need to be made even stronger by metal incorporation into our composites or metal reinforcing metal, or when we have strong parts that need to be optimized for weight, like substituting continuous carbon fiber in for metals or striving for economical and optimized designs, preserving metal only where it is absolutely necessary. So anytime that you find that your requirements for your application are just above or just below metals or composites and need to shift in the other direction without fully making the leap into the totality of the part being produced in the other technology or process, that's a good time to start looking around and seeing if hybrids may benefit from that process. Also, in analyzing that with the simulation software and the simulation capability within Eiger that was just rolled out for trial and is still in active trial for all Eiger users, that's a great way to determine what the strength of your individual configured prints are at this time and decide if additional elements or an alteration of your design might be necessary. Now, the other side of the equation, just as important, are the times when it does not necessarily make sense to hybridize. If the operational specifications of a particular environment, such as temperature or solvent resistance, or geometries that are required are not going to be conducive to the incorporation of a composite into a metal part, then that may not be a good idea or an optimal occasion to use this hybrid approach. It may be better to look at the rest of the geometry or push further into designing for additive, DFAM, at the part or at the assembly level and determine if a macro change will fit the bill. The same thing goes for metals. Just using metals for the sake of metal may not be necessary, although that goes equally for traditional manufacturing as it does for additive. The temptation to lean into what we know and the over-design based on past experience is certainly strong. The other situation is when not to hybridize is when we absolutely have critical tolerances, and as a result of potential tolerance stacking in creating a single part may prevent dimensional alignment or interface with higher assemblies or with obtaining the positional precision that may be required. Also, if there's access to the capability of post-processing and precision machining single part prints such that all tolerances and functional features can be met, then hybridizing may not be of benefit there either. So from this point, my charge to all of you is to drive to hybridize, or at least consider. Encourage yourselves and your peers to think with additive, to look at parts as they are currently manufactured, turn them on their head and see where hybridization may in fact be beneficial, or may significantly improve not just the parts, but the way in which we engage with your print systems and your design, production, and assembly processes today. Remember that hybrids and assemblies are not necessarily inherently weaker. Just because we're combining pieces together and possibly moving away from a monolithically printed part does not necessarily mean that we are weakening those parts. If you recall a part such as those end-of-arm gripper jaws, when you have multiple walls stacked against one another, where the composite portions meet each other, particularly improvement in the strength and the rigidity of the parts themselves. Add in features like dovetails and route fiber through those dovetails. Combined with ideal geometries and splitting, this allows for much larger assemblies to be created while maintaining their strength, as well as properly orienting the parts and fibers for the application. In approaching large part requirements, stop to consider what might be accomplished with stronger, better assembled parts, rather than simply large, non-optimized single prints. Not only that, but with more printers leveraged in tandem, larger engineered parts can be ready faster as well. Parallelizing of manufacturing can also bring parts from idea to life much more quickly and allow for that utilization of assemblies or of ideal geometries based upon the needs of the application, rather than simply a traditional method being framed around a traditional method of manufacturing. Adding additional capabilities within this envelope, adding material capabilities to composites, or bringing composites technology to bear alongside metals can help increase the overall realization of value, both in time and in part performance. If you're looking for guidance in approaching your current and future challenges through this expanded lens of additive, then definitely reach out to your local resources. This can be a good way and a perfect time to examine your past challenges and to determine if there might be ways to find greater success by addressing those challenges with a different approach and tools such as these available within additive and the Digital Forge specifically. Our extensive reseller network, all staff trained application engineers who are versed in our print systems. We also have multiple application engineers internal to Markforged, as well as additional resources that can provide guidance on realizing the full potential of your Markforged print systems. The greater availability and access to Markforged University is another way to dive deeper into learning great ways to take further advantage of the Metal X and the Markforged composite printing technologies. Markforged is deeply invested in providing education to all industries on the possibilities of additive manufacturing and the ability to bring to reality all of the solutions that you can imagine today. All right, thank you, folks. So we'll pivot to answer some questions. Do drop those in the chat. Let's see. All right, so we've got one question here. So any possibility of 3D printing material reactions with metals causing corrosion? So this is definitely one that I know has been brought up in certain applications, specifically aerospace. I know was a big one. There's a lot that goes into things like carbon fiber and aluminum and those types of interactions. A lot of it depends on design interfaces. I know there's kind of the specific keep outs within those types of industries, and there's a few different ways to work around that. One is kind of having an interstitial printed portion, and that's actually a really great application for printing because you can very easily achieve kind of those conformal spacers, right? Rather than necessarily having like blanketing. Coatings is another one. So we actually have a few white papers out there and working documents on things like coatings to achieve certain applications. So that's a great question, and there's a few ways to step around it, and again, reaching out to design resources, certainly. All right, let's see. Mechanical properties well documented, bond strengths of dissimilar materials. So that's another great one. So as far as the overall mechanical properties, so I think there's two things here. One is, we certainly have the mechanical properties of our base materials, and then the simulation portion of how strong are the parts. So that is a big part of why simulation has been rolled out, right? One of the questions that we often get is how strong are the parts that we can print? And simulation is a great way to get down the road of solving that. Certainly not necessarily a replacement for high-end CAD packages, but getting a good understanding of how strong parts are today in application relative to what we need. One thing that we've found out a lot of is the trend to over-design parts, just like throwing metals at it or things along those lines. As far as bond strength, so we do have several documentation and recommendations on things like adhesives, if that's what we're looking for. For the most part, we tend to favor more mechanical lockups when doing when creating kind of more monolithic parts from multiple pieces. Press fit. So Onyx is a great material for press fit for things like if we need to put hardware into a part that's not necessarily conducive with mid-print geometry insertion. So if I've got like a captured nut that I want to place into a part, but it's going to be in such an orientation that I can't insert it comfortably and still have print head clearance as it's printing, then I may look at designing in pockets or certain voids into a part and then inserting that hardware afterwards and then capturing it in place with things like press fit plugs or other kind of geometric retention features. Dovetails are another great one, especially if you've got larger pieces where you can have things like offset overlapping dovetails in order to capture that. So a lot of the bond strength is going to, and the kind of interfacial strength between portions of a larger part are going to depend on the geometry involved. Definitely stuff that we can provide guidance on. We do have some things there, and that's actually something that I think would be great for additional resources of specific features. So joining features is a great one. That's a great question. Let's see. So we've got one. So preservation of the overall strength of a large printed assembly. So again, depends on the application, depends on the materials being used. So in some cases, where it's favorable to be able to route. So this, and I'm seeing this with applications around like FX20, for instance, where we now have a larger print bed that we can route continuous fiber throughout the entirety of the part. So the same questions come into play as far as optimization of orientation and placement on the print bed. So if I can potentially print it all in one on a larger print bed and get continuous fiber routed where I want it in a beneficial manner throughout the entirety of the part, then you're going to get a lot of strength out of that specific part. The times when I might trend toward printing kind of a larger part in multiple pieces are, several of the things that we covered. If there's drives that are beyond just the strength of the part, like if it's a temporal pressure of getting a part quickly, whether from prototype or whether to fit the application, that might be one. But as far as purely on part performance, if we've got varying load cases, or if we have specific geometry that we need to preserve that might require positioning on the print bed in such a way that we can't get really good long continuous paths of fiber. So if I'm going to have to split it up that way, that's often when I'll look at potential retention features or things like, hey, can I insert a metal threaded rod or pressed large pins or things like that in kind of cross geometries, and then be able to orient my fibers specifically within specific portions of the part on the overall. As far as things go, testing empirically, we've seen a lot of, very positive overall strength results, especially relative to the weight of those finished parts, in kind of the empirical cases. Simulation case, it gets a lot more complex, but within a few iterations, typically have seen a lot of those applications addressed thus. Excellent. So we talked a little bit about the joining of two parts. So, again, interlocking geometry combined with things like pin retention, threaded hardware, that type of stuff. Mostly depends on the load case and the geometry and real estate involved. So if I have the space to insert things like those retention features, whether dovetails. So shrink fit is floated here. There's usually not a huge amount of overall shrinkage, at least in printed nylons like onyx or nylon white, which are the majority of what we have been printing from a legacy perspective. When you bring in things like TPU, for instance, there's still not a huge amount of shrinkage, but that can be one where you have compressibility. So if you have stuff like gripper ends or conformal features that need to interact with something and remain non-marring, that's a great way where the internal geometry of the TPU portion can be controlled in order to facilitate that compressibility, and then pressing those together, that just that general compression can hold those in place. But on the whole, there's a whole host of potential options. We do have some stuff in our design guides, which are available through the support site, or can easily be forwarded from any of your reseller or Markforged contacts. Let's see. So here's a good one. I think this is more let's see, more pertinent to metals specifically, but there's a little bit on the composite side. So I'm going to try and address both. So the question is, so how to take care of thermal expansion of additive parts within a hybrid assembly. So, and whether annealing or tempering might need to be done for additive parts prior to assembly. So I'd say so I'll take the second half first, and then I'll go back to the first half. So the second half being annealing or tempering being required. So I find that more relevant to kind of the requirements of the application. So if we're doing something like cutting operations, right? If I've printed a blade or a cutting surface, or if I printed a high wear surface like a press brake or a bending apparatus, I would approach that, particularly if I'm looking at it from a metals perspective, I would look at the post-treatment or those types of processes from the perspective of what's necessary for that application, from that kind of contact surface. If I need high toughness, or if I need high hardness, I would kind of address that specifically. As far as on the overall, with those types of parameters affecting the overall hybrid part, usually I'll try and take a step back, and when I'm working with either internally or with end users on the potential requirements of an application, I'll try and take a step back and a holistic approach to what are the bulk requirements of what we need to accomplish here, right? So is it a high temperature environment? Is it a case where, you know, that thermal expansion may come into play? From an Onyx perspective, this is often why, you know, I'll incorporate continuous fiber, specifically carbon fiber, into a lot of these portions of assemblies, or these hybrid parts, things like fit check apparatus, or CMM fixtures, or things for quality, because the CTE, for despite nylon's properties, right, the bulk within Onyx, the CTE control that I can get in the stiffness aspect, in the rigidity, and kind of that minimal shrinkage from that carbon fiber, and controlling the overall geometry of the part, is fairly significant. So the other one is properly routing fiber in those cases, right? So one thing I will say is our default in Eiger is, you know, particularly for like isotropic fibers, is just kind of a continuous rotation. I always recommend matching layers, being able to control stiffness through approaches like that, where we go in and we specifically route the fiber, or the rotations or the orientations of that fiber, keeping them along flat planes within a part, for kind of maximized geometric control over the overall. So you know, if you've got dissimilar materials, CTE is always going to be something that needs to be kind of thought about and managed, tested if possible, but there's definitely ways to control it and approach it. Let's see, possible to print just a metal coating into common casting parts? Ooh, that's a really good question. So as of right now, we're not looking at, you know, kind of printing like cladding metals, but you know, anytime we're incorporating metal into parts, you know, definitely something to kind of approach from an overall of how we're kind of interacting with those parts on the finish. So it's probably a little too broad to go with a blanket answer, but on a case-to-case basis, looking at, you know, how to orient a metal part and still preserve the geometry that's necessary, like a surface finish. Like if I'm doing a conformal part, minimizing the amount of supports that are required, so orientation of that metal part in order to go through the process is definitely critical. Let's see. Okay, here's another one. Okay, so we've got fairly new user. Let's see. Limits to the types of fibers that can be used. Are polymer fiber types also options besides Kevlar? So in the Digital Forge, the Markforged overall ecosystem, specifically on the composite side, so we've got several polymers. As far as incorporation with fibers, we've got Onyx, which is by far the most used, as well as the various other flavors of Onyx. So FR, the fire retardant version of Onyx, ESD, the electrostatic dissipative version of Onyx, that used in electronic assembly and any time where we need a dissipative plastic. We have nylon white, so a base unfilled nylon material, little less rigid, and a little softer on kind of the exterior surface. And then we also have PLA, but that does not incorporate fiber routing. And then we have TPU, which at this time does not have fiber routing, but certainly can be incorporated into these overall assemblies. Then on the continuous fiber side, right, the differentiator from Markforged is that capability for continuous fiber routing. So the 4 fibers that we have available. So continuous carbon fiber for high strength, high rigidity. If I have a part that I need to, say, replace aluminum, or replace a high strength plastic, and I want very high rigidity but very lightweight, potentially gaining more in that lightweight capacity by having, carbon fiber incorporation, but then potentially use of infill. That's kind of the prime driver there. We also have two flavors of fiberglass. So standard fiberglass, where maybe I don't need carbon fiber strength, but I need something that's stronger than just standard FFF plastics, right? So PETGs, PLAs, base nylons, that type of stuff. And then high strength, high temp fiberglass. So kind of filling the space between just the standard fiberglass and carbon fiber. So it makes a significant leap upward, not to carbon fiber levels, but maintains a good amount of cost savings there as well. And also where I might need to retain strength at temperature, because you'll get another 10 to 15 degrees C of kind of stiffness and heat deflection temp capability. So that's usually where we'll see HSHT, or high strength, high temp fiberglass used. And then Kevlar would be the last one. So there's 4 fibers capable, kind of different tools for different applications, right? The different punches and hammers in the toolkit, proverbially speaking. Kevlar is great for if I need to allow for progressive failure. So rather than kind of a step function of a part snapping, if I need that part to be able to stretch, distend, and experience that plastic deformation before ultimate failure, Kevlar is a great one. If I need something like a bump stop, a wear surface, Kevlar is great for those types of applications. All of that covered pretty well in a lot of our documentation and design guides. So definitely dive into those. If you need some more guidance, definitely reach out to any of our resources. We're certainly happy to help guide you there. Let's see, Chris. Oh, great to see you, Chris. Let's see, annealing practical to achieve better properties, or does carbon fiber do a good enough job? I'm assuming we're talking about the polymers and the composites specifically. Have not seen a huge amount of applications with plastics, specifically like onyx, for instance, where annealing is really a major consideration. But that could also be a limitation of my experience and knowledge. So, Chris, I know we already talked, so I'd love to hear anything that you see in that realm. Where I have seen annealing come into play more is more of the higher temp plastics. So when it comes to stuff like, the current availability of like Ultim 9085 filament that's available on the FX20. That's certainly something that could be looking at annealing capabilities there. Any of the other potential high temp plastics that we may see coming down the pike for roadmap. So nothing announced, but as we see additional materials added to the FX20 library, plastic annealing, whether incorporated into the print process or as a post process, certainly could come to bear. I'd say it's more of an application specific basis. Nothing right now projected as far as doing things like simulation on that front. So right now testing would be mostly pushed to empirical verification, but definitely something to consider on more of a case-by-case basis. Let's see, recommendations of printing around an existing part in the print volume. So as of right now, there's not a whole lot to incorporate there. But if you're talking about like multiple materials in a single build that the part is capable of, definitely bring that up with any of your local resources. So your reseller or any Markforged folks that you might be talking to, because these types of potential demands for capability, or where that provides an additional edge within these systems, would be great to hear more about. So these are the types of applications that certainly get my team really excited about what we can do today and then what we can potentially do tomorrow. So as of right now, no kind of multi-material printing available beyond the base polymer and a continuous fiber. But if that's something that's significantly valuable, we want to hear about it. So do we have a branch in India? So we don't have specifically a branch, but we do have coverage in India. So we have a great applications engineer who's based in India. We do have some of our APAC team that is over in India, as well as resellers. So our reseller network, our partner network is global. We do definitely have resources there. So definitely reach out, contact through the website if you don't already have folks that you're already speaking to. So let's see. And if you are based in India, thank you for joining. Definitely appreciate the global presence here. Let's see. All right, so here's a good one. So would love to see more data on strength or stiffness across layers, so that Z or Z strength height. Cheat by using screws through layers, not always practical. Our hybrid. So definitely a hybrid. You're definitely doing a hybrid there. I'd say maybe not cheating. You're just that's called good engineering. But let's see, as far as things go. So this presentation will be shared out. So this will be available for reviewing. We did record this this presentation in this session, so it will be out there. Definitely great questions though. So on the predicting strength and stiffness, absolutely. So that's where simulation. Do try using the simulation tool. So when you are in Eiger, you can just, I forget the exact path, but look for the simulation trial. There should be a path to be able to get that. For the next several months, that will be available. So take your parts, run them through that simulation, drop in your load case, and you can see what the overall strength of the part is, or what your factor of safety is relative to your anticipated load case of the part. We do have several trainings and a few videos and things that are available. Again, reach out to your local resources. They can certainly help guide the conversation. If you need more assistance, then definitely let us know, because simulation, it's a fantastic and readily usable tool, especially for folks who may not have a lot of experience with FEA or finite element analysis. So it's kind of a very good initial take on getting your load cases of the part. So understanding that stiffness, deflection is one of the characteristics that is simulated for in those types of applications. So definitely reach out, definitely make use of that tool. That should get you some good understanding, and keep using those cross pins where you need to, as far as things go. So again, thanks for joining. So great to have some UK representation here. All right, let's see. Can any material be impregnated with epoxy, etc.? So this one's another good one. So porous after printing. So there are plenty of things that can be done in these types of applications. A lot of it comes on the design on the front end of things. Definitely have seen some applications, and this is both in metals and in composites printing, of being able to like fill voids and things like that. I've seen a lot more in the way of like coatings, like dip coatings or spray coatings as far as things go. But as far as kind of take up of the part, so a great one, if you're looking to like entirely fill something like with an epoxy, consider using stuff like the gyroid infill option. So gyroid infill has that kind of continuous sinus curve capability within the part. So instead of those little triangles or hexagons within the part in that vertical orientation, you get that constant rotation isotropically throughout the entirety of the part, and allows for continuity throughout most of the part, depending upon your kind of external shell geometry and how complex it is. But if you need to flow something throughout the entirety of a part, whether to fill it, whether to allow for airflow or any other things through that part without necessarily using things like exposed infill, which I do believe is a feature that's been released. So there's a couple of different ways to do that. Definitely something that I think we could probably do a little bit more highlighting of, as far as the capabilities and usage of that gyroid. So that's certainly something that I will re-radiate, but definitely take a look at that gyroid infill relative to the parts that you have today. Excellent. Awesome. We've still got quite a few people still hanging on. This is great. We've gotten to basically the end of the questions here. Very much appreciate the attendance of everyone who was here today. If you have any questions about anything here or any of the other webinars or capabilities, or if you have an idea for something that you think would be great for us to highlight or address on the materials, hardware, applications perspectives, please definitely reach out, get that passed in through our various social channels, or any of your Markforged contacts, reseller or Markforged direct. We'd love to hear from you, and we'd love to understand what it is that we can help provide some education and thought-provoking content on in order to utilize the systems. Awesome. Well, thank you everyone for attending today, and we will close it up with this. Thanks so much.